Lectures 19 and 20, chapter 14, solutions. So we continue to talk about solution. Titration. Titration of 10 milliliters of HCl solution requires 15 milliliters and of known concentration of sodium hydroxide solution to reach the end point. And we need to determine the concentration of unknown HCl solution. So first let's check what is the ratio of this reaction. So HCl plus NaOH, we know it will give us sodium chloride and liquid water, and everything else is soluble. So when it is 1:1 mole-to-mole ratio, we can use V1 M1 equals V2 M2. In other words, we can write 10 milliliters, 10.00 milliliters of HCl times unknown molarity of HCl equals known volume of sodium hydroxide times known concentration of sodium hydroxide. And molarity of HCl equals 15 times 0.1 divided by 10. So milliliters and milliliters cancelled, and we'll get moles per liter. And this is 0.150 because we need three significant figures, M of hydrochloric acid. But in case it is not 1:1 mole-to-mole ratio, we can do it other way. We can start with volume of known reactant. And we don't need to convert it into liters if we have volume of the second reactant also in milliliters, because these 2 milliliters will cancel each other. So we start with what is given about the second reactant, for which we know both volume and concentration. 15 milliliters of NaOH, and we know molarity 0.1 mole of NaOH in 1 liter. We know that 1 mole of sodium hydroxide reacts with 1 mole of hydrochloric acid. So now we got rid of moles of sodium hydroxide. Now we have moles of HCl per liter, and we know that 10 milliliters, that this amount of moles of sodium of hydrochloric acid was in 10 milliliters of HCl solution. So these milliliters and these milliliters cancelled. Moles of NaOH cancelled, and we have moles of HCl per liter, and that's what we need. And again, you can see that the same 15 times 0.1 divided by 10, 0.150. This is molarity of HCl solution. Now, suppose we got some titration data about titration of KHP with unknown sodium hydroxide solution. So in this case, we titrate solid potassium phthalate with sodium hydroxide. So we have 3 results of 3 titrations, and we need to calculate average molarity of sodium hydroxide solution. So Now we need to calculate molarity for all three trials. So for the trial number 1 or number A, we start with what is given, 0.283 grams of KHP. And first we need to convert it into moles. Molar mass is given, 1 mole of KHP is 204.22 grams per mole. So now we have moles of KHP. We know it is from our manual, we know that 1 mole of KHP reacts with 1 mole of sodium hydroxide. Now we have moles of sodium hydroxide. And to calculate its molarity, we need to divide number of moles by the volume. We know that volume of sodium hydroxide solution in this case was 1156 milliliters. But molarity, it is moles per liter. So we need to convert these milliliters into liters. 1 liter, 1000 milliliters. So grams and grams cancelled, moles and moles of KHP cancelled, milliliters and milliliters cancelled, and now we have moles of sodium hydroxide per liter. So we have a unit that we need. And after we multiply and divide all of this, we'll get 0.119875 moles per liter of NaOH, which is molarity. So now suppose we calculate it the same way, right, for all three trials, and we get these results for A, B, and C trials. Then we can calculate average. If we add all three results together and divide by 3, we'll get this number, which is our average. And our initial numbers contain 3 and 4 significant figures, so we need to round our final answer to 3 significant figures. So average concentration of sodium hydroxide solution based on these 3 titration results is 0.120 moles per liter of sodium hydroxide. Now let's talk about pH. So what do we need to remember about pH? First, we need to remember that H3O plus times OH minus is called water ionization constant, and this product equals 1.0 times 10 to the negative 14, no units. But hydronium concentration, hydroxide concentration, and all other concentrations, when it comes to pH and equilibrium, should be in moles per liter, only in moles per liter. So if we have grams per liter, percent, something else, we need to convert it. First thing, we need to convert it to moles per liter. Then, based on this, if we need H3O plus, we can divide water ionization constant by the concentration of hydroxide ion, and we'll get concentration of hydronium ion, or other way around. If we need hydroxide concentration, we will divide 10 to the negative 14 by hydronium concentration. pH always equals negative decimal log of concentration of hydronium ion. The same way POH equals negative decimal log of the concentration of hydroxide ion. And if we add pH and POH, it will give us 14. Now for pH, we use the following rule. To determine number of significant figures for pH, we should look at the number of significant figures for concentration, and it should be equal to the number of decimals. So if, for example, concentration of H3O plus is 0.105, 3 significant figures, our pH for this solution should be some number before decimal point, and then 3 decimals. Should contain 3 decimals. So, and finally, if we need to go from pH to concentration of hydronium, or from POH to concentration of hydroxide, we should use antilog. So H3O plus equals 10 to the negative pH, and OH minus equals 10 to the negative POH. So using all these equations, we can easily solve the following problems. So pH is given, we need to calculate H3O plus, so we'll use this equation. H3O plus, always 10 to the negative pH, or 10 to the negative 3.23, and it is 5.89 times 10 to the negative 4, and unit is molarity or moles per liter. Now, number of significant figures. pH contains 2 decimals. So we need to round concentration to the 2 significant figures. So it should be 5.9, 2 significant figures, times 10 to the negative 4 moles per liter. pH, similar problem. We have pH, we need to calculate both H3O plus and OH minus. So let's start, because we have pH, let's start with hydronium concentration. It is 10 to the negative pH, 10 to the negative 13.23, or 5.9 times 10 to the negative 14. And OH minus hydroxide ion concentration we can calculate 2 ways. There are 2 ways. First way, we can divide water ionization constant by the concentration of hydronium ion, which we already determined. Or we can calculate POH, which is 14 minus pH, and then raise 10 to the power of negative POH. So let's go this way. POH is 14 minus pH, or 0.77, and hydroxide ion concentration 10 to the negative pH, 10 to the negative 0.77, and it equals 0.17 moles per liter. We have concentration of hydronium ion. We need to calculate pH. pH negative log of H3O plus negative log of 1.5 times 10 to the negative 2, and it equals 1.82. We have two significant figures. We need two decimals in our pH. So hydroxide ion concentration is given. We need to calculate pH. Again, two ways. We can first calculate H3O plus using this equation, and then take negative log of it. Or second way, we can calculate pOH as 10 as negative log of 1.0 times 10 to the negative 4, which is 4.0. And we have two significant figures in our pH, in our concentration, so we need two zeros. 4.00. So this is pOH. Now we can calculate pH, which is 14, and we use the same number of decimal places as for pOH. 2 zeros minus 4.00, so it is 10.00. And pH and pOH, they don't have units, they are unitless. pH of 0.02 moles per liter hydrochloric acid solution. So just to remind you that in the water solution, strong acid dissociates completely and give us H plus, which is the same as H3O plus, and chloride ion. So if we have 1 mole, it will give us 1 mole. It is 1-to-1 mole-to-mole ratio. 1 mole of hydrochloric acid gives us 1 mole of hydronium ion solution. Now, so concentration of H3O plus equals concentration of HCl and equals 0.02 moles per liter. And now pH, negative log of 0.02, and it is 1.699. We have just one significant figure, so we need one decimal, 1.7. Number 8. pH of diprotic acid, sulfuric acid. So what is different for the sulfuric acid? When it dissociates in water, it would give us 2 moles. 1 mole of sulfuric acid would give us 2 moles of hydronium ion and 1 mole of sulfate ion. But we are interested in hydronium ion. So each mole of sulfuric acid gives us 2 moles of hydronium ion. So if we have 0.02 moles per liter H2SO4, it means that 1 mole H2SO4 gives us 2 moles of H3O plus. So concentration of H3O plus will be 0.04 moles per liter of hydronium ion. And when we know concentration of hydronium ion, we can easily calculate pH. So it is negative log of H3O plus, negative log of 0.04 or 1.398, and because we only have one significant figure, we need to leave one decimal, so it's going to be 1.4. So if you compare, you will see that for the monoprotic acid with the same concentration 0.02, pH is less acidic 1.7 comparing to 1.4 for the same concentration of diprotic acid, because diprotic acid gives us 2 moles of hydronium ion per each mole of sulfuric acid. Now let's try to solve a limiting reaction problem and calculating pH of final solution. So we know that for all limiting reaction problems, we should start with writing and balancing reaction. We have a hydroiodic acid plus potassium hydroxide. Products are potassium iodide and liquid water. Everything else is soluble. So it is 1 mole, right? Reacts with 1 mole and gives us 1 mole of potassium iodide. Now let's calculate how many moles of both reactants we have. So 0.3 liters times 0.2 moles per liter gives us 0.06. I will not count significant figures now. I will count it at the end. 0.06 moles of HI. And as for potassium hydroxide, it is 0.15 liters times 0.4 moles per liter, also 0.06 moles. And what does it mean? It means we don't have limiting reactant. They will react completely both. So acid will be completely neutralized by the base. And final concentration of both acid and base, so they both will react completely. Final concentrations of both will be 0, and the same number of moles of potassium iodide will be formed. So our final amount of moles of potassium iodide is the same 0.06. If we would need to calculate its concentration, we should calculate final volume, right? 0.3 liters plus 0.15 liters, and then divide by the total volume to calculate molarity of our final solution. But we need to calculate its pH. We know when concentration of H3O plus equals concentration of hydroxide ion. So when it is neutral water, we know that pH is 7. So pH is 7, and the only thing we need to add a required number of zeros. We have 3 significant figures. in all these numbers, so we need 3 decimals. This is our supposed final pH. So this one is a little more complicated. Now, again, as always, let's write and balance reaction. So it is diprotic acid, sulfuric acid plus sodium hydroxide gives us sodium sulfate and water. And we need to balance it. Now it is balanced. So in this case, 1 mole of sulfuric acid requires 2 moles of sodium hydroxide. Okay, let's calculate number of moles of both reactants. First of all, let's convert milliliters into liters. So we know that 500 milliliters, it is 0.5 liters. The same here. 500 milliliters, 0.5 liters. So 0.5 liters, 0.5 times 0.1 molarity gives us 0.05 moles of an acid. And 0.5 liters times molarity 0.4 gives us 0.2 moles of a base. So we have 0.05 moles of sulfuric acid and 0.2 moles of sodium hydroxide. Now we have to decide which one is limited. So 1 mole of sulfuric acid requires 2 moles of sodium hydroxide, meaning that 0.05 moles of sulfuric acid times 2 would require 0.05 times 2 would require 0.1 mole of sodium hydroxide. So only 0.1 mole of sodium hydroxide will be used. And sulfuric acid will be used completely because this is our limiting reactant. So final amount of sulfuric acid 0, and this is our limiting reactant. And this is excessive reactant. Now let's calculate this excess. We have initially 0.2 moles, 0.1 mole will be consumed in reaction, so will be converted into sodium sulfate, and 0.1 mole of NaOH will be left. And amount of sodium sulfate which will be formed. So 1 mole of sulfuric acid produce 1 mole of sodium sulfate. So 0.05 can produce 0.05 moles. But we are not interested in sodium sulfate, we are interested in pH. And for pH, we need concentration or of hydroxide ion or hydronium ion. Because our final solution contains base, it means we can calculate concentration of hydroxide ion. So what is the volume? It is 0.5 liters plus another 0.5 liters. So it is 1.000 liters. So when we divide 0.1 mole by 1.0 liters, we'll get 0.1 mole per liter concentration. Now let's look at significant figures. 4, 4, 4. So we need 3 more zeros to keep required number of significant figures. And this is final molarity of NaOH. Each mole of NaOH contains 1 mole of hydroxide ion. So concentration of hydroxide ion in our final solution, and don't forget volume of our final solution is now 1 liter. So concentration of hydroxide ion is the same as concentration of sodium hydroxide, and it is 0.1 moles per liter. So we can calculate POH, which is negative log of 0.1 or 1.0, and we need 4 zeros because we have 4 significant figures. And pH equals 14. In fact, this is too many zeros. We can never get this accuracy for determining pH, but it is just theoretical. So 14 minus POH, 14 minus POH, so it is 13, and we need to keep 4 zeros. So this is our pH, and we can see it is basic, right? It is close to 14. So this solution is basic because we have excess of a base, not of an acid.